Deep beneath the English Channel, one of the most ambitious engineering projects ever attempted is about to begin. Using Earth-eating robotic monsters, 13,000 workers are about to embark upon an epic quest to build the longest undersea railway tunnel in the world. This historic journey will push the limits of technology and human determination to the breaking point. Some workers will not survive. But the creation of the Eurotunnel is a story of triumph, one of this century's greatest superstructures. Ever since the Ice Age ripped them apart 10,000 years ago, a small finger of ocean, the English Channel, has been the only path between England and Europe. Throughout history, countless lives have been lost trying to cross this treacherous body of water. For centuries, amateur designers and skilled engineers alike have tried and failed to create a safe, permanent link.
The first channel tunnel design, if you can call it a design, was in 1802. But at that time, the technology was so limited that really it was science fiction.
But by the end of the 20th century, the line separating technology and science fiction is rapidly disappearing. It is now possible to create machines the size of large buildings, machines that can literally move mountains. Inside factories like these, engineers begin experimenting with space-age technologies to take humans into new and potentially dangerous territories. Soon, an age-old question is asked once more. Can a tunnel be created under the English Channel? But does England herself even want such a passageway? From the days of Camelot to the age of Churchill, the Channel's cold, choppy waters formed an imposing barrier between the monarchy and its enemies. Would-be conquerors from Napoleon to Hitler developed plans of how they could first defeat the English Channel and then England itself. Ironically, during World War II, Adolf Hitler developed a plan to dig a tunnel near the captured French town of Calais, site of the modern-day French Eurotunnel station. It was a threat the Allied forces took seriously.
Bomber pilots were requested to report any plumes of grey material in the channel, and they actually established soldiers along the coast here with listening devices trying to detect any sounds of tunneling.
But with the defeat of Germany in World War II, Europe entered a new era. The sounds of war were replaced by the sounds of commerce. By 1986, one-time rivals England and France decide the Channel has become an economic barrier, an obstacle that must be eliminated. To achieve this, the French and British governments dedicate themselves to the task of building a modern marvel, the world's most technologically advanced undersea tunnel. Engineers and business people alike dream of high-speed rail trains traveling beneath the English Channel, carrying the citizens of a united Europe into newfound economic opportunity. But before the first shovel of dirt is even dug, the project seems destined for failure.
This was a nightmare at the time. We had to decide on things which we didn't really know about. And one example, which I always quote, is, what diameter do you want for the tunnel? Now, you would think that this was something that had been decided before, but it hadn't. And the contractors kept pestering us, saying, what size tunnel do you want? And we said, well, listen, we just arrived. I don't know.
For as long as we can all remember, people have dreamed of a channel tunnel.
As this ad, seeking Eurotunnel investors, points out, the project was financed solely by private investment, with an original price tag of over $10 billion. This made it very different from other large engineering projects of this century, like New York City's Lincoln Tunnel, which was government-funded. Ultimately, Eurotunnel had to answer to its shareholders. But despite the private backing, there was much public opposition, especially on the British side. Some opponents were concerned about the environmental impact of the project, while others didn't want to surrender England's status as a proud island empire. The project's decision-making body, a consortium of 10 companies called Transmanche Limited, or TML, is undaunted. They plan a design of 3 parallel tube-like tunnels. When finished, these massive tunnels will form a railway loop between England and France. Engineers envision a system that will carry thousands of passengers and hundreds of tons of freight each day on this circular 30-minute trip. Of the 35 miles between the French terminal at Calais and the British terminal at Folkestone, 24 will be undersea. No other project has ever attempted to tunnel this far in such a hostile environment.
There are lots of problems, technical problems. How will a car move inside the tunnel? What kind of trucks can I transport? You know, all the variety of things.
As the project begins in late 1986, all of these questions remain. But before issues regarding the tunnel's operation can be addressed, the most daunting and obvious problem must first be solved. A machine that can chew through more than 30 miles of solid rock, hundreds of feet below the sea, doesn't exist. It will have to be created. Thousands of miles from the English Channel, on the outskirts of Seattle, Washington, a solution is being forged of iron and steel. Here at the Robbins Company, a firm specializing in heavy mining and tunneling equipment, the next breed of super machines is being created. In this colossal factory is a mechanical beast that dwarfs its creators. It's called a tunnel boring machine, or TBM. When finished, this giant snake-like earth mover will be over 800 feet long and weigh over 1,500 tons. Its rotating head, almost 50 feet in diameter, consists of hundreds of cutting edges made from tungsten carbide, one of the hardest materials known to man. These will be the teeth of this mechanical monster, the cutting force it will use to chew through the earth below the channel. Pushing the machine forward is a series of powerful hydraulic devices called rams, which will drive the cutting head through the rock. The millions of tons of excess rock it will dig up, called spoil, will be carried out on conveyor belts through the TBM service train attached to the cutting head. The challenge of carving tunnels through solid rock has always pushed the boundaries of our engineering and manufacturing skill. Even today, it requires a rare balance of brain and brawn. When large-scale projects like the Los Angeles Aqueduct System were being created in the 1930s, tunneling technology was in its infancy. Today, the Robbins Company will replace blasts of dynamite with a computerized mechanical marvel of which the early pioneers could only dream. But the danger these modern miners face will also be unparalleled. At its deepest point, the tunnel will be 246 feet below the seabed. During construction, if their boring efforts create a crack in the tunnel or cause a leak, the force of the incoming water will be equivalent to over 7,000 tons of falling weight. Man and machine would be crushed in an instant. At the Robbins Company, frightening scenarios like these must be addressed. Project organizers selected the tunnel's route precisely because it goes through a layer of chalk called marl, which is well suited to their tunneling efforts. It is also the last remnants of the original land bridge that once connected England and France over 10,000 years ago. While this chalk is ideal for tunneling on the British side, the situation on the French side of the channel is far more treacherous. Here, the seabed is riddled with faults and fissures, conditions that could lead to the deadly accidents engineers must try to prevent. Of the 11 TBMs that will be created for this mission, the machine that will be used on the French side faces the most difficult job. Working at greater depths, in parts of the seabed that are far less stable than the British side, this undersea giant will have to withstand pressures twice as intense as any tunneling machine has ever experienced. So engineers decide to create a special TBM that is part boring machine, part submarine. When finished, it will be able to withstand the same amount of undersea pressure as a World War II sub. Finally, the technology behind the dream of reuniting the European continent seems to be in place. And while the project will ultimately link England and France, the massive construction process will be an international effort. Companies from Germany to Japan will add their technologies to the mix, making the Eurotunnel a truly global undertaking. While this international force rallies to overcome the physical obstacles of the channel, there are other challenges already mounting. Namely, the race to complete the tunnel on time and on budget. It is now December 1987. This is where the Eurotunnel begins. 2 huge shafts at Sangatte, France, and Shakespeare Cliff in England. Too enormous to be delivered to the site as complete machines, the first TBMs are lowered piece by piece into the darkness of the shafts 200 feet below. Going with them are the workers, the men behind the machines. They too are descending into the unknown, taking the first steps of an epic journey. As the first work begins and the light of day slowly disappears, there is an air of hope, expectation, and much uncertainty. While extraordinary safety measures have been taken to protect the workers, it remains a dangerous world. And for some, the greatest civil engineering project of the 20th century will carry the ultimate price tag. As giant mechanical earth eaters are given a final check before being lowered to their work site hundreds of feet below the ground, one of this century's most ambitious engineering projects is underway. The creation of an undersea railway that will link England and France begins here in Sangatte, France, and here at Britain's Shakespeare Cliff, near the site of the future Folkestone Terminal. What officials hope will someday be the world's premier railway system is now just a hole beneath the earth. The race is on. Compounding the awesome challenge of the actual tunneling operation is a human challenge. British and French workers, once bitter rivals, must now learn to work together. Once they reach the dark and dangerous caverns deep below the earth, there can be no room for cultural misunderstandings.
A French engineer is trained to make a plan. They can't start work unless they can see what there is to be done, see where their task fits into the whole thing, and see how it's all going to be organized as it goes along. No such thing in the British culture. British culture is to sit down and say, now what have we got to do, chaps? And sort out who's going to do what and set to work.
One of the first problems they face is the assembly of the giant tunnel boring machines, which the workers christen the moles. Even the smallest machine takes months to build and costs several millions of dollars. The largest of these subterranean titans weighs 1,500 tons. Because of their enormous size and weight, the TBMs must be assembled on site, which in this case is far below the earth. The actual cutting head of the TBM is just the tip of its immense body. Attached to it is the service train, a multi-car train system that carries the hydraulic power to drive the TBMs forward. When connected to the cutting head, each service train is a staggering 850 feet long. One of the service train's main functions is to be a conduit for the removal of millions of tons of rock and sediment these mechanical moles will dig up. The debris will be carried by conveyor belt through the service train to a supply train and back, and finally to disposal facilities in England and France. The removal of the spoil is a major challenge. When operating at full speed, engineers estimate the TBMs will cut through 750 feet of rock per day, removing 2,400 tons of waste per hour. When the project is finished, the total amount of rock removed would fill a major football stadium 13 times. But equally important as taking material out of the tunnel is the challenge of getting materials in. And one of the most crucial building blocks at this underground work site are the 500,000 concrete slabs which will line the tunnel walls. Because these concrete rings will provide a life-saving barrier between passengers and the churning English Channel above them, their construction is of utmost importance. Special factories are built in England and France to manufacture these vital sections. Each ring is made of specially reinforced concrete, even stronger than the concrete used in nuclear power plants. It is also reinforced with a framework of steel rods for extra resistance. This is necessary because the savage ocean pressure that will bear down on the tunnel walls is equivalent to 12 atmospheres, or 12 times the pressure we feel on the surface. No human could survive under such immense force. Once the rings are finished, they are transported by narrow gauge railway to the TBMs in the tunnel and brought up through the service train. Then, a remarkable display of mechanical symmetry takes place. As the spinning head of the machine claws its way through the rock, operators using giant cranes create the tunnel walls, right behind them. After being fitted into place with incredible precision, a gap of only 3/4 of an inch remains between each section. This tiny space is then sealed with a cement grout, and another piece of the tunnel wall is complete. When finished, each ring of the tunnel will weigh 40 tons. But just as the skeleton of the tunnel is beginning to take shape, the project suddenly seems in danger of falling apart. It is now 1988. The British and French teams are starting with the middle service tunnel, drilling towards each other to meet in the middle of the channel. But by May, the giant tunneling machines begin to break down.
It was designed to operate at pressures that no machine had ever operated before. It was strictly a prototype as a result of the fact that it was so complex and nothing like it had ever been built. It had all kinds of troubles. Practically everything important on the machine failed or broke at one time or another shortly after we installed the machine.
On the French side, the TBMs are encountering precisely the scenario engineers feared the most: hidden faults and fissures in the seabed. On the other side of these cracks lie the awesome forces of the English Channel.
It was technically very difficult because the water pressure that we had to work in, as the machine bored forward, it bored right through faults that were filled with seawater, connected directly to the ocean.
Waterproofing measures designed to protect the TBM's delicate electronic equipment from the seawater fail, stopping the giant machine in its tracks. Then, as engineers scramble to repair the electrical problem, another even larger problem develops.
This is the seal we intend to use. It's a wire brush type seal.
The ring of watertight seals providing a life-saving barrier between the TBM and the tunnel walls also begin to fail. Again, victims of saltwater corrosion. Engineers need a solution, and fast. The corroded brush-like lining seals are replaced. Then, a mixture of paper and special grease is applied to the brushes. When this coating comes in contact with seawater, the paper particles expand and create a permanent, watertight bond between the segments. The TBM is once again waterproof. But to Robbins Company President Richard Robbins, the tunnel wall seemed far more secure than the legal agreement he is working under. Soon he is forced into a desperate personal gamble.
The French contractor knew that we had designed a prototype machine that we didn't really understand exactly what it was going to cost us to build. So he built into the job some interesting incentives that if we met certain project construction points along the tunnel by certain dates, we would earn bonuses. But it was so bad in the early stages that I was really almost betting the entire company that we would succeed. So it was a big risk for a small company like ours.
But it isn't just contractors like the Robbins Company who are gambling their future. Because the entire project is privately funded, Eurotunnel officials must hit their own deadlines to continue to receive funding. With each new delay, the entire fate of the Eurotunnel lies in the balance.
The one thing we all understood was that if we stopped, it would be very hard to restart. The relationship with the banks, the problems with the contractors, the difficulties with the governments, or just plain organizational difficulties of whatever kind, would very probably bring an end to the project.
Finally, engineers are able to redesign the mechanical flaws in the French TBM and move ahead. But they are now 9 months behind schedule. To make up the time, both the British team and the French team must stay on course. But how will these mole-like machines, tunneling towards each other from opposite directions, maintain such a specific course? They are far too deep below the Earth for high-tech satellite mapping to be of any use. And even the slightest deviation in their course, a fraction of 1 degree, will mean they fail to meet up under the channel. To remain on track, tunnel engineers use a space-age laser beam guidance system. Here, a red laser emits a beam from behind the cutting head. As it sends a beam of light forward, it hits various control points fixed to the tunnel wall before striking a special target on the rear of the cutting head. These control points feed information provided from the laser straight into the machine's onboard computer. From the TBM control cabin, operators can now adjust the hydraulic rams that thrust the TBM forward and keep it precisely on the right course. But even if the two machines do stay on course, the complex plan for after they meet has never been tried before. As the French and British TBMs tunnel towards each other, they will reach a designated point where they will stop. They will now be a mere 100 yards apart. At that point, a long steel probe will be sent through to determine if they have been truly on course. If so, more conventional equipment will finish the relatively short distance that remains. But if the two machines are off course, it will mean yet another delay while engineers try and come up with a solution. And with the project's skyrocketing budget under fire, more delays could signal the end of the dream called Eurotunnel. (1989). The year begins on a positive note at the Eurotunnel construction sites. The earlier problems with the French tunnel boring machines seem to be solved. One of the giant TBMs even sets a world tunneling record. For almost 3 years, work on the tunnel has progressed without a fatality. But in the first days of a new year, a time usually associated with hope and new beginnings, tragedy lies just around the corner. On January 20th, in the dark recesses of this massive cavern, the tunnel claims its first victim. 19-year-old engineer's assistant Andrew McKenna is walking half a mile down the tunnel beside the narrow-gauge railway tracks used by the supply carts. Apparently failing to hear an oncoming train, he is suddenly crushed to death by a locomotive carrying spoil from the site. Without warning, the stark reality of their dangerous jobs becomes clear to every worker. The tunnel has claimed one of their own. Even with 20th century technology, the job of building tunnels remains extremely hazardous. While workers cope with the loss, they also have to deal with other day-to-day fears brought on by the tunnel.
At the pumping stations, they actually went underneath the tunnels, and there would be like a little tunnel under the main tunnels, so the trains would be going above you, and you could be down working in 3 foot of water in a little cross passage with a blank wall with nowhere else to go, and that could be very claustrophobic. And we actually experienced people being sent in to work with us who were and found out they're claustrophobic. And then it became a little bit scary because you had to say to them, look, you can't work with us down here, you're terrified of the situation, and you had to think of everybody else's safety. It was dark, it could be dusty, so you had to be able to cope and have a sort of positive outlook, really.
Even with the most rigid of safety standards, the death of Andrew McKenna will not be the last tunnel casualty. In all, 12 people will die in this historic and sometimes tragic undertaking. And while the mood of the workers has turned suddenly dark, the tunnel itself remains unchanged. Here, it is always dark. Workers who refer to their machines as moles are left wondering if they are the real underground creatures.
You could be on a day shift where you arrived at work 5 o'clock in the morning and it was pitch black. You could go into a tunnel, work all day in darkness or semi-light, not bright, and then you come out at 5 o'clock at the end of your day and it was dark again. So you could go a whole week without seeing daylight. And that was a very weird experience because, you know, it's daytime and yet you never saw it.
As workers move forward in the darkness below ground, above them, work continues on the high-tech trains that will use the system when it's finished. The new service being created exclusively for the Eurotunnel is called Le Shuttle. Tunnel officials say the name is an example of the Anglo-French cooperation that characterizes the project. When finished, Le Shuttle trains will carry passengers in their cars on a continuous loop between the Folkestone terminal in England and the Calais terminal in France. In plants like these, workers use more than 10,000 welds to mold more than 5,000 parts into the single shell of a train car. Each Le Shuttle train is being specially built for the frequent trips and heavy loads it will haul. To provide maximum power, a 132-ton locomotive is placed at each end of the train.
They have to be very special trains because the trains themselves are half a mile long and they have a lot of cars inside them or a lot of trucks, and therefore the locomotives have to be very powerful. They're the most powerful locomotives in the world.
Each of these locomotives must be capable of pulling a 2,400-ton train by itself. For this kind of power, they will draw upon 25,000-volt electrical cables. This high-voltage energy source provides the equivalent force of a 7,600 horsepower engine, about 100 times the power of an average car. While the shuttle trains have the most powerful locomotives on Earth, the sleek Eurostar trains have the world's fastest. The Eurostar passenger line uses the popular TGV trains, which will travel from Paris to London at speeds of 185 miles per hour. While in the tunnel, the trains will travel at more subdued speeds, approaching 100 miles per hour. Because the transporting of commercial freight will be so important to Eurotunnel's economic success, huge new rail cars are designed to transport heavy trucks. Each freight shuttle, also a service of Le Shuttle, will have 28 carrier wagons like these. Each carrier wagon can accommodate a truck weighing up to 44 tons. Below the earth, there is no finished railway for any train to travel upon. But that is about to change. It is now October 30th, 1990. There is a new feeling in the air today, a feeling of expectation. After 3 years of tunneling, the British and French TBMs digging the service tunnel, which will run between the two rail tunnels, have arrived at their undersea destination. Facing each other under the English Channel, 100 yards apart, the machines have stopped their digging. It is strangely quiet. the same question races through each worker's mind. Have they lined up? A probe is sent through. There's a tense silence. Each worker at every level of the project knows it will be a catastrophe if the tunnels are off course. This would be the type of mistake that could fuel the flames of anti-tunnel sentiment into a raging fire. Finally, they get the news. The tunnels line up. England, by virtue of a 100-yard pole, is no longer an island. After boring through 23 miles of solid rock, the tunnels are only off by 20 inches, well within the acceptable safety margin. It is a momentous achievement. While the project's workers, a unique collection of specialists from across the globe, revel in their victory, a celebration is quickly planned for the face-to-face breakthrough. Since there is still a 100-yard gap between England and France to close, it is decided that the official breakthrough of the service tunnel will take place on December 1st. As workers return to their jobs with a new sense of accomplishment, a lottery is held to pick one worker from each country to meet in the completed tunnel. Meanwhile, there is the problem of what to do about the last 100 yards. It is too expensive to retrieve both the French and the British machines, so a unique solution is developed. The British aim their machine downward and effectively commit mechanical suicide, burying the high-tech behemoth deep into the earth. This allows the French TBM to move forward and connect with the British side of the tunnel. December 1st, 1990. Finally, the moment of truth arrives. A thin layer of chalk, essentially a prop for this massive media event, is now all that separates Frenchman Philippe Cosette and Englishman Graham Fagg. With a couple of well-directed jackhammer blasts, a barrier that has stood for 10,000 years is gone.
They're through. Hey! There's the handshake we've all been waiting for, Mr. Fagg and Mr. Cosette.
One of the most ambitious engineering efforts of the 20th century climaxes with a simple gesture of goodwill. Hundreds of feet below the English Channel, a Frenchman and an Englishman meet through a small hole. For the first time since glaciers ripped them apart thousands of years ago, France and England are once again linked.
The atmosphere was absolutely electric down there, not only just at the breakthrough but afterwards, and people were moving. We all felt European. I don't think anybody felt English or French. We were all European at the instant and for the brief hour before we could actually set off back to our respective sides. Amazing scene, really wouldn't have missed it for anything.
The next few months will hold many more extraordinary moments. The public gets their chance to share in history with the above-ground breakthroughs. First in France, and then in England.
When that tunnel broke through, there was a party that would end all parties. It practically went all night. It was at the Windsor Castle on the British side. Fireworks and feasting and about 1,000 guests, and it was really a marvelous party.
What I remember is sitting down there, having the feeling there is no more machinery running now, and a feeling in amongst the most tremendous uproar, popping champagne corks and backslapping and cheering and so on, a feeling of absolute silence. It was the most extraordinary feeling.
But amidst the revelry and the silence, the realization begins to sink in that there is still a long way to go. 2 more tunnels need to be created, not to mention the installation of the high-speed railway. Work on the Eurotunnel is far from over. As the parties celebrating the breakthrough of the service tunnel fade away, efforts to complete the 2 remaining tunnels resume at an energetic pace. The 2 main rail tunnels are called running tunnels. To allow trains to switch from one track to another, massive crossover caverns are carved from the seabed. 40 feet high and over 500 feet long, they are the largest undersea caverns ever created. Workers refer to these massive structures as cathedrals, but in the event of a deadly fire, they could quickly become a scene of mass terror. To prevent fire from spreading from one running tunnel to the other, engineers build giant doors to separate the 2 tunnels. Each door is made from super strong carbon manganese steel. Then, a half-inch layer of flame-resistant material is added. These fireproof walls are a movable fortress, weighing over 100 tons each. But fire isn't the only emergency tunnel officials must prepare for. Terrorist attacks, bomb threats, and even the remote possibility of an earthquake are all scenarios which must be planned for.
The evacuation train will be with us in approximately 6 minutes' time.
Specially trained security force and evacuation teams are established that constantly rehearse emergency procedures. While they speak the same language in times of emergency, French and British officials still have different beliefs regarding issues of safety.
There are 2 different safety philosophies. The French have a belief in intelligent operators using sophisticated equipment, but in charge of the equipment. The British have a culture of fail-safe computers. Channel Tunnel, you've got an aggregation of both, so you can be quite sure whichever you think is better, the tunnel's got it.
No other tunnel in the world is as safe as this one, with the central service tunnel, the fire supply systems, duplication of power supplies, emergency walkways, and all the procedures that have been put in place to cover every eventuality.
But there is one eventuality engineers haven't planned for. As engineers perform test runs in the tunnels, the friction of the trains is producing an enormous amount of heat, raising temperatures to a scorching 140 degrees Fahrenheit. Scrambling for a solution, engineers create a pipeline filled with chilled, flowing water to keep the heat in the tunnel from accumulating. This cold water acts like a sponge to absorb the tunnel's heat. The water, now very warm, is then pumped to a cooling station on shore, re-chilled, and recirculated once again. Elsewhere, the 2 stations that will serve as Eurotunnel's passenger hubs are beginning to take shape. The massive French terminal at Calais is one of the largest construction projects in the world. Within its sprawling 11-mile perimeter, the Calais station will have 30 miles of roadway and 30 miles of railway track. While the British terminal at Folkestone is tiny in comparison, 5 times smaller than the French station, it will house the nerve center of the entire Eurotunnel system.
Cross passage door 5650. You'll cross the opening. Stand by, please.
Here in the Folkestone Command Center, operators use state-of-the-art technology to control all of the rail traffic that moves through the tunnel. Sitting behind 3 rows of desks, they can survey a curved wall showing the status of the entire system. This high-tech display is called a mimic board. It shows the position of every train in the tunnel and at the terminals.
Door clear, opening now.
In the event of a power failure, tunnel control will immediately switch over to the Calais Control Center, which is staffed at all times in case of emergency. Even the drivers of the shuttle trains will receive a little high-tech help. In this driving simulator, operators practice navigating through the tunnel. In real life, the driver of each shuttle will sit in the front locomotive, while the captain of the train sits in the rear locomotive. The captain, who is ultimately responsible for the safety of the passengers, communicates with the driver by intercom. But the onboard computers also have command status. If the train begins to move too fast, the shuttle brakes will go on automatically. By the middle of 1991, the project's infrastructure is beginning to take form. From the terminals to the trains themselves, it is beginning to look like the dream of an undersea rail link will be realized. But deep underground, two more hurdles remain. The completion of the northern and southern rail tunnels. On May 22nd, the first of those obstacles disappears into history as the Northern Running Tunnel is finished. This is the tunnel that will carry passengers from Britain to France, but today it is a symbol of a united Europe. Just over a month later, on June 28, 1991, more celebrations as a huge crowd gathers for the completion of the Southern Tunnel. The last TBM punches through the remaining wall and comes to a stop. 4 years after the digging began, one of the most difficult engineering challenges in history is now complete. While workers celebrate and drink champagne, the machines finally fall silent. In the long, colorful history of these two countries, this is a singular moment. French or British, project chairman or supply cart driver, for a moment, it doesn't matter.
What is being created here and what has been achieved to date is of enormous value for the future of both our countries and of Europe. Thank you.
In all, over 13,000 workers have labored for more than 6 years. Besides the 3 main undersea tunnels, each over 30 miles long, 9 other smaller access tunnels were also created. The amount of material removed on the British side increased Her Majesty's kingdom by 75 acres. Engineers believe the hard part is over. In fact, contractors like Richard Robbins collect bonuses for finishing ahead of schedule. But when today's party is over, tomorrow morning will usher in the stark reality of a bloated budget and an uncertain future. To Eurotunnel officials, the hard part may have just begun. With the digging of the Southern Railway Tunnel finished, the 7-year struggle to build the world's longest undersea tunnel nears completion. The narrow-gauge railway tracks which carried supplies into the tunnels are replaced by a new concrete floor. This will support the wider, standard-gauge railway tracks on which high-speed trains will travel at 100 miles per hour. Over 300,000 rubber shock absorbers are installed to secure 60 miles of track. The powerful locomotives that will pull trains half a mile long 20 times a day are delivered to the terminal at Calais, France. Finally, on May 6, 1994, the grand experiment is about to begin. After boarding one of the luxury Eurostar trains in London, Her Majesty Queen Elizabeth II arrives in Calais, France. This will be just the first part of an all-day celebration scheduled in both countries. Her Majesty is received by French President François Mitterrand. After a ribbon-cutting ceremony, the Queen and the French President depart in Her Majesty's Rolls-Royce to travel on Le Shuttle back to England. The image is a powerful one. Not only are the former adversaries the Eurotunnel's ceremonial first passengers, they are also the public image of the new European, able to cross a once formidable barrier with grace and ease. Arriving back in England for the second phase of the ceremony, Her Majesty takes time to greet each crew member honored with making this historic inaugural journey. But as the ceremonies and the media attention fade away, so does the public's interest. Initial usage of the tunnel is far below expectations. Critics of the Eurotunnel's costs, now almost $21 billion, are again on the warpath. Less than 2 years later, evening broadcasts spread the news officials feared the most. An accident has happened in the tunnel. On November 18, 1996, fire rips through a freight train bound for England, 11 miles from the French entrance. Trapped in smothering fumes for nearly half an hour, passengers ignore requests to wait for help and abandon the train, groping their way to safety in the service tunnel. The fire is so hot, it transforms the cargo of mammoth trucks into unrecognizable lumps of melted steel. 8 of the 34 crew members suffer smoke inhalation, and the tunnel is badly damaged. What has been called the safest tunnel in the world is now brought to its knees. Amid a firestorm of public controversy, the Eurotunnel is closed. 1,500 feet of railroad track and 150 feet of the tunnel's concrete lining are wrecked and need to be replaced. The damage caused by this accident, estimated at almost $100 million, makes it one of the costliest rail accidents in history. While no one was seriously injured, public confidence in the tunnel plummets. Eurotunnel officials go on the defensive.
12 hours later, nobody was in hospital. Yet there'd been a 1,500 degree centigrade fire 300 feet away from them. Nobody was in hospital. Now say that about a highway crash, or about a ferry sinking, or about a plane crash. You can't.
17 days later, Eurotunnel officials stage an emergency evacuation exercise designed to reassure the public the tunnel is safe. A drill critics say has more to do with public relations than public safety. Despite this disaster, the northern tunnel reopens to passenger traffic several weeks later. But the badly burned section of the southern rail tunnel is closed for 6 months while the damaged tracks are repaired. Finally, commercial freight traffic resumes on June 15th, almost 7 months after the accident. As this disaster fades from the headlines, memories of the accident slowly fade with it. But what hasn't gone away is the sacrifice made by over 13,000 men and women who created this architectural marvel. This plaque at England's Shakespeare Cliff pays tribute to the 12 workers who lost their lives working to create the Eurotunnel. Theirs was the ultimate sacrifice. But thousands of workers also gave a great portion of their lives to work far below the earth, cut off from their families and the rest of the world.
My son was 1 when I started on it, and when I finished he was 6. Now I do feel I missed a major part of his growing up by being on the tunnel.
The job of being a tunneler, of staring at a mountain or ocean and seeing a way to cross it, has always required a special type of person. A person who can exist without natural light. In suffocating holes, working for long periods of time towards a seemingly impossible goal.
Tunnelers are a special breed of people. They move around the world building holes in the ground. Most of their work is never seen by anybody else, but they do take a pride in building a good tunnel.
It remains to be seen whether or not the Eurotunnel will be a financial success. But officials say immediate financial return was not the sole concern of every investor.
The philosophy of the investors was not, curiously, mostly financial. They said it doesn't matter whether we don't see any return. We think the benefits for our children, our grandchildren, are going to be extremely important.
The Folkestone Terminal in England and the Calais Terminal in France are now ports of call to thousands of travelers. This undersea journey, for centuries the subject of scorn and ridicule, now seems routine, the shortest distance between 2 points.
If you were British and you lived here, we're an island, and if you want to get off this island, in the past, the only way is either to get on a boat or to fly. And for the first time ever now, you can take a train. You don't have to change, you don't have to get off. You get on the train in central London, and you get off, and you're suddenly in central Paris, and it's a whole new culture.
Whatever brings these travelers to England or France, the size of the world they lived in before the Eurotunnel is smaller now. A physical barrier that has stood for 10,000 years is gone. Europe is already more united.
Whatever the political structures, whatever the legislative structures, the economic and social coming together is unstoppable. And it's happening, and the tunnel plays a key part in that, and is symbolic of it.
The Eurotunnel remains one of the greatest engineering achievements of this century. For the thousands of men and women who built this tunnel, it stands as a monument to their belief that the impossible is simply a challenge, a temporary obstacle that can be overcome with technology, skill, and perseverance.
Having lived with it for the last 10, 12 years, I feel something special about it every time I come in. I'm quite amazed by the amount of work that went into the tunnel, the complexity of all the equipment, and the short time that it took to build this modern wonder of the world.
In the end, the Eurotunnel may be viewed as more of a bridge than a tunnel. As these high-tech trains speed beneath the ocean, crossing cultural barriers as they go, the free exchange of new ideas they carry with them will remain their most precious passenger.